This image shows one small portion of our night sky as viewed from the Hubble telescope. Within this image, we see multiple galaxies, each composed of roughly 100 billion stars. As vast and mysterious the universe may seem, it is governed by fundamental concepts. For example, the vibration of electromagnetic waves, such as light, X-rays, and ultraviolet, travel across our universe and do so according to an oscillation called simple harmonic motion. Simple harmonic motion can help us to understand our universe on the galactic scale and all the way down to the atomic scale, as we see here in the vibration of a CO2 molecule. Simple harmonic motion occurs when a restoring force, such as in a spring, is directly proportional to the displacement of an object. So the condition for simple harmonic motion is that the force is directly proportional to the displacement. An excellent example of this is a mass on a spring. The greater the displacement from equilibrium, the greater the force. So the maximum force occurs at the high and low points where the spring is most compressed and most stretched, and the force is zero when it passes through equilibrium. Simple harmonic motion in a spring exhibits wave motion. If we imagine the oscillator moving through space, a wave is produced. Even circular motion and pendulums can act as simple harmonic oscillators. If we rotate an object that's moving in a circle, we can see its motion viewed in 1D resembles that of a mass on a spring. So circular motion shows simple harmonic motion. Here's a pendulum oscillating back and forth. Just as with the spring and circle, we can see that the motion of the pendulum exhibits simple harmonic motion. By rotating our view, we can see how this resembles wave-like behavior. We've now seen how simple harmonic oscillators can produce and exhibit wave properties. The three types of harmonic oscillators are the mass on a spring, an object rotating at a constant speed in a circle, and the pendulum. We will use the pendulum to explain the fundamentals of wave behavior, which include period, frequency, and amplitude.
A pendulum swinging back and forth is a wave-like behavior. Today we're going to use a pendulum to demonstrate three fundamental characteristics of waves: period, frequency, and amplitude. Period is defined as the time it takes to complete one full cycle.
And a cycle is when you go from here all the way out here and all the way back again. And that's one complete cycle.
Again, period is the time it takes to complete one full cycle. We can use a timer to measure the period of Miss Bates.
This amount of time is the period.
Period.
Okay, so we shorten the rope. Let's see how that changes things.
Yeah, with
ready?
a shorter rope, let's see what the period is this time.
Okay, are you ready?
Ready.
You have to reset this. Alright, here we go. Whoop. Oh wow, that was a lot shorter.
Yeah, your period is only 3.5 seconds with a shorter pendulum.
Okay, so what does that mean? Shorter time means...
That means the frequency will be greater. You'll complete more cycles per second.
Huh. Alright, let's figure that out.
Let's calculate and see if that's true.
The period of Mrs. Bates was 3.5 seconds. That is, the time it took her to go there and back again. We now want to know how many times or cycles she completes in 1 second, and this is called the frequency. Since period is the time for one cycle, and frequency is the number of cycles in a time period, we say that the period is the inverse of the frequency, or T equals 1 over F. To calculate the frequency, we put the period into the formula and take its inverse. You can do this with the 1 over x or x to the minus 1 button on your calculator. Then all we need to do is box those puppies up. So, as the pendulum length decreased, so did the period. But as period decreased, the frequency increased.
All right, I think we got it all.
Yep, we're all set.
All right. Oh, we forgot to do amplitude.
Oh yeah, we forgot about amplitude.
All right, why don't you tell them what amplitude is?
Amplitude is how far a pendulum swings from equilibrium. It's a measure of maximum displacement.
So here I'll have a small amplitude. And back.
That time you didn't swing very far from equilibrium.
No, but here I'll have a big amplitude. Woo! Now that's a big amplitude.
For a mass on a spring, the maximum displacement occurs when the spring is most compressed at the top and most stretched out at the bottom. So amplitude is the maximum displacement from equilibrium. For a pendulum, equilibrium occurs at the bottom of the swing. So the amplitude is the displacement from equilibrium to the maximum height, which occurs on either side. All right, that's a wrap.
Yep, I think we're all set. Oh, we forgot to tell what the unit for frequency is.
What, the unit for frequency?
Yeah.
Ow! Ah! That really hurts.
Oh, I think the units hurts.
Oh! Yeah.
Are we done?
I think so.
Did we not remember this conversation? Are you pulling? I'm
Yeah. Okay, you can go now.
Go where?
Like, let go. Go out and just
I'm gonna
swing.
swing up against a rock.
No, you're going to swing this way.
Conservation of energy.
Don't you teach physics?
Yes, if I go there. This is the real world, though. Remember the whole physics land deal we had?
All right, go ahead.
I'm not.
That's it. Now go off the rock.
Can I sit down?
Yeah.
Yeah.
Oh my god! I can't get back up on this stupid rock.
Well, Joel can grab onto you.
Yeah, Joel's just sitting there.
Okay, perfect.
Christian,
So
I'm not.
red.
Joel.
The red dot's
I'm not
there.
going.
Yeah.
I'm not. You're gonna knock the rock down. Christian, no, no. This is just so unsafe. And now what happened? Now we're stuck here. Good job.
Yeah, we're stuck here forever.